We learned yesterday about the photoelectric effect, discovered in 1887 by, anybody?
Einstein.
No.
Hertz.
Yes, I was going to say it hurts me that you don't know the answer to this. It is Hertz. Hertz tried to explain it, as did a bunch of other people, but they couldn't explain it properly. There were several observations that were made that just didn't match the explanation. Here's what happened. When light strikes a metal, sometimes an electron is ejected. Hertz and his contemporaries argued that if an electron was being ejected, then it was because there was sufficient energy in the light to cause the electron to be ejected. That part of the argument is actually right. But what they argued is that if it didn't have enough energy to cause an electron to be ejected, you got more energy by having more light. You get more energy by having more light. In other words, if you had one flashlight and electrons weren't being ejected, well, then get two flashlights. Or if you had a dim flashlight and electrons weren't being ejected, then get a brighter flashlight. Or if you shone a flashlight on a surface for 1 minute and electrons weren't being ejected, then shine it on the surface for 5 minutes. The problem was that didn't cause electrons to be ejected. When we looked at the observations, the data that was taken, didn't matter how much light was shone on it, electrons wouldn't be ejected if electrons weren't ejected in the first place. It wasn't the intensity or the brightness or the amount of light that mattered, it was the frequency. But nobody could figure out why it was the frequency that mattered until 1905. 1905 and Einstein, good.
Nice.
Hertz used classical theory to try to explain the photoelectric effect, and that didn't work. Einstein used this new theory that he called Photon Theory to explain how this worked. And guess what? It explained beautifully the observation. A photon, Einstein defined as a what? A quantum of energy. We think of it as a particle of light, a little bundle of energy, but the actual definition is a quantum of electromagnetic energy. The energy of a photon is not related to the intensity or the amount of light that we have. Rather, it's related to, according to Einstein, the type of light that we have. So in other words, if you have red light with a certain frequency, that has a lower energy than blue light does because it has a lower frequency than blue light. You can have just a little bit of red and a little bit of blue. Blue will be more energetic, not because there's more of it, but because the frequency is higher. It's also equal to hc over lambda. So Einstein is saying this. Electrons aren't being ejected if you have a certain amount, if you have a little bit of low frequency light. They won't be ejected if you have a lot of low frequency light. That matched the observations. Einstein said if you increase the frequency to a higher value, you're increasing the energy to a higher value, and then you have more chance of electrons being ejected. And guess what? The observations match that. So in 1905, this little-known patent clerk in Switzerland who came up with this photon theory explained something that couldn't be explained by anybody. This is the evidence that he needed to support his photon theory. Remember we talked about wave theory? We said diffraction, interference, refraction, polarization. Now we have evidence for the particle theory or the photon theory of light. Now remember, Einstein isn't saying that the wave theory is gone now, that we're discounting all that. He's just saying that we're adding to that. Not only is light a wave now, light is also a particle. It's a wave and a particle. Just like sometimes I behave, talked about this analogy yesterday, sometimes I behave like a father, sometimes I behave like a brother. I have a dual nature, a dual reality in a sense. Sometimes an electron, sometimes a photon, sometimes light behaves like a particle, and sometimes it behaves like a wave. All right, two quick terms, and then we're going to give you a little summary of what we've done, and that's the table that I handed out to you a few minutes ago. The threshold frequency. The symbol for that, by the way, the threshold frequency is F0. Yesterday we talked about the pain threshold. The pain threshold, we said, is the amount of pain that's required for you to feel it. Some people have a higher pain threshold than others. Okay, if I apply a stimulus on somebody's arm, it may or may not hurt somebody. If it's below the pain threshold, it doesn't hurt. If it's above the pain threshold, it hurts. Threshold frequency is kind of similar. If we have a photon that is below a certain frequency, the threshold frequency, then nothing happens. If it's above the threshold frequency, something happens. But it's not the feeling of pain, rather it's the ejection of an electron. So we're going to say the threshold frequency is the minimum frequency necessary to eject an electron. The minimum frequency necessary to eject an electron. That kind of goes along with another term, the threshold wavelength. But it's not F0, it's lambda max. This is not the minimum frequency necessary to eject an electron, rather it's the, it's the maximum wavelength necessary to eject an electron. If you have a certain photon that's below a certain frequency, nothing's going to happen. If it's above a certain wavelength, nothing's going to happen. You need to be above the frequency, you need to be below the wavelength in order to cause an electron to be ejected. Now that also goes with a third term that we call the work function. The work function is the minimum energy necessary to eject an electron. The energy that gets used up in the process of ejecting the electron. Now, on the last page, we said E is equal to HF, which is equal to HC over lambda. If E is HF and HC over lambda, then minimum energy, or W, would be equal to H times the minimum frequency. H times F0, or HC over what? What is it? Lambda max. Now I'm going to square off these two sides of the equation because those are the two that appear on my data sheet. The last one doesn't appear on my data sheet, but it's not that hard to figure out, right? If E is HC over lambda, then W must be HC over lambda max. Now the table that I handed out to you a few minutes ago is going to summarize the effect of changing some things here. So I want to go through this to make sure that you understand the qualitative aspect of the photoelectric effect, what happens, the observations that were made, and why they, and how we explain those observations, and then we'll go on to a little bit of math with this. So we get two columns here. The first column says the photon is below the threshold frequency. We'll say F is less than F0. Or lambda is above lambda max. Let's fill in all four of these blanks here. Let's assume that we're increasing the frequency of the photon. We're still below the threshold frequency no matter what, but we increase it while staying below the threshold frequency. What happens? What is it? Nothing. The answer is nothing. If we're below the threshold frequency, doesn't matter what we do to the frequency of the EMR, as long as we stay below, nothing will happen. No electrons will be ejected. It's kind of like this. You got a little car over there on the side of the road. Just a small little two-door Civic. A truck is going down the road. The threshold, there's a collision between this truck and this car. The threshold for knocking this car off into the ditch is 50 kilometers per hour. If the truck hits the car at 30, it doesn't knock it into the ditch. If the truck hits the car at 40, it doesn't knock it into the ditch. If the truck hits the car at 49, it doesn't knock it into the ditch. If the threshold is 50, it doesn't matter what you do when you're below the threshold, you're not going to knock it into the ditch. If the photon is below the threshold frequency, it doesn't matter what we do to the frequency, we're not going to knock it into the ditch, or we're not going to cause the electron to be ejected. What if we increase the wavelength? What is that the same thing as doing? Yeah, we're lowering the frequency. Think about what that means in terms of our analogy. My truck was going at 30 kilometers per hour. The threshold was 50 to knock that little car into the ditch, right? What if I decrease the speed of the truck now to 25? Nothing. What if I decrease it to 15? Nothing. I'm not going to knock the car into the ditch, right? If I lower the frequency, then certainly nothing will happen. No electrons will be ejected. What if I increase the intensity, which just means more photons? If each one of them has insufficient energy to eject an electron, then it doesn't matter how many of them we have, nothing's going to happen. If we're below the threshold frequency, we can do whatever we want. As long as we stay below the threshold frequency, you will never get an electron ejected. You will never get a current, an electric current generated here. What if the photon is above the threshold frequency? Let me give you the answer, the general answer to all four of these blanks, and then we'll get a little bit more specific. The general answer is this. If you're above the threshold frequency, something happens for all four of these. But can we be a little bit more specific here? Do you have a question or an answer? Okay. No, if it's equal, then you're going to eject the electron. The threshold, we talk about that pain threshold again? Yeah. If we talk about that pain threshold again, if you meet that pain threshold, you don't have to be above the pain threshold. If you meet that pain threshold, then that's going to hurt. So we're above the threshold frequency here. The car is on the side of the road. The truck is hitting at 60 kilometers per hour. We're above the threshold frequency. Guess what? The car gets knocked into the ditch, right? But what if we increase the frequency or the speed of the car, the truck, I mean? Let's make it 70, 80. What happens to the car? Does it still go into the ditch? Yes, but it goes faster into the ditch. So what happens here when a photon strikes it above the threshold frequency with an even higher frequency, we're going to eject an electron with a higher energy. It's still a 1-to-1 ratio. Remember that one truck will knock one car into the ditch. One photon will eject one electron. Just remember that the electron will be more energetic if the photon is more energetic. What if we increase the wavelength while still staying above the threshold frequency? Somebody told me, I think it was Jacob, told me that increasing the wavelength decreases the frequency, or was it Parker? It was Parker? Okay, sorry. Giving Jacob all the credit for that.
Sorry, Jacob.
Parker says increasing the wavelength decreases the frequency, and you're right. As long as we stay above the threshold frequency, decreasing the frequency decreases the energy. So that's like saying we're taking the truck from 60 to 55. Are we still going to cause the car to go into the ditch? Yes, but the car will have less energy as it goes into the ditch. So we're going to still eject an electron. But this time with less energy. Still a 1-to-1 ratio. One truck causes one car to go into the ditch. 20 trucks causes 20 cars to go into the ditch. One photon causes one electron, albeit a less energetic electron. 20 photons causes 20 less energetic electrons. What if you increase the intensity of the EMR? You're above the threshold frequency. You're going to cause an electron to be ejected. But if you have more photons, more trucks, what are you going to do? You're going to knock more cars into the ditch. More photons will cause more electrons to be ejected. Remember, it's a 1-to-1 ratio. 20 photons, 20 electrons. 15,000 photons, 15,000 electrons. If you increase the time of exposure, that's the same thing. More photons. You're going to get more electrons ejected. It's a 1-to-1 ratio. Now, more electrons being ejected just means, can materialize, can manifest itself into a higher electric current. If we design a solar cell that generates electricity when light strikes it, that's because electrons are being ejected and then harnessed through an electric circuit. If you have more electrons ejected, then you're going to get a stronger electric current. So sometimes what you see in this context is slightly different wording. It might not say more electrons ejected. It might say a higher electric current produced. Really, the electric current is a measure of the number of electrons that are flowing per second. So you can say more photons causes more electrons, or you can say more photons causes a higher current generated. Sometimes we call it a photocurrent, the electric current that's generated by the photoelectric effect. All right, quick little reminder, E is equal to HF equals HC over lambda. Both of those are on my data sheet. W is equal to H times F0 equals HC over lambda max. Part of that is on my data sheet. Let's define two more terms now and derive a couple more equations that are good for the photoelectric effect. Stopping potential. Symbol for that is capital V, stop. This is an electric potential. The electric potential required to stop an electron, it's already been ejected. I'll explain that in a second. The photoelectric effect has occurred. A photon of sufficient frequency has caused an electron to be ejected. We may be doing a test to see what the threshold frequency of a metal is. You're designing a solar cell. You want to know what the threshold frequency is. Maybe you're just working in a lab and you want to know what Planck's constant is. You're doing an experiment with the photoelectric effect. One of the ways that you can do that is to cause the photoelectric effect and then stop an electron by a potential difference once it's been ejected. We did that before, not in the context of the photoelectric effect, but we did something real similar to this back in Unit 2. Remember the charged particle was slowing down in an electric field, like a car going up a hill? That's what we're doing here, right? We've got a car going up a hill. We're stopping an electron that's been ejected. If you remember, that car that was going up the hill had kinetic energy at the bottom of the hill. As it went up the hill, the kinetic energy decreased and something increased. What was it? Potential increase. But it wasn't MGH potential, it was QV potential. So we're going to say the kinetic energy of this electron that's been ejected, we'll actually call it the maximum kinetic energy of this electron that's been ejected, is Q times the stopping potential. I'm going to square that off because that's on my data sheet. But I'm going to also add another part to that equation. It's kind of on my data sheet, but in a different place. EK max of the electron that's been ejected is QV stop, but it's also equal to 1/2 mv squared, of course. And finally, by the law of conservation of energy, the initial energy should be equal to the final energy. What is it that provides the initial energy in this whole deal? What energy is coming into this problem? No, not kinetic energy. Let's not say kinetic or potential. What is it that has the energy? The light, the photon. The energy of the photon is H times F. So we're going to say the initial energy here is HF. What energy comes out of it? What is it that has the energy that comes out of it? The electron. What kind of energy does the electron have? Kinetic energy. Although when we're talking about the photoelectric effect, we always call it EK max, the maximum possible kinetic energy. The reality is, though, there will be energy lost in the process. So what we start with won't be equal to what we end up with. What we start with will be equal to what we end up with, plus the amount that we used up in the process, which is equal to the work function. So we're going to say HF is equal to EK max plus W. I'm not going to box that off because it's not on my data sheet. But I'm going to highlight it because it's important. Either be able to figure that equation out like we just did, or memorize it, because you will use this. Probably more than any of the other equations, actually. Which isn't very fun because it's the one that's not on our data sheet. Wouldn't EK max be determined by W? Yes, it would.
So then why do you add W?
Well, if the initial energy, let's just pick numbers, no units. Okay, the initial energy of the photon was 10. 10 what? 10, doesn't matter, 10. 10 units of energy. If W, if the amount that was used up was 2, then the electron could have as much as 8 left over. But if the work function, the amount that was used up was 4, then the kinetic energy could only be as much as 6. So your question was, isn't the kinetic energy affected by the work function? Absolutely it is. Yes, there's energy that's used up as it gets ejected. And the more that gets used up, the less is available for the electron. Right? The more, go back to our truck-car analogy for a second, the more energy that gets used up in the collision, right? The more energy that, that goes into deforming the car, the less energy that you have left to push the car into the ditch. Just going to put a little note here that this equation applies to what I call the 5-second rule. And we're going to come across that right after your break, where we use this in a problem. The 5-second rule, my 5-second rule says this. It's not when you drop a piece of bread with peanut butter on it and it lands face down, you have 5 seconds to pick it up and eat it. Rather, my 5-second rule says this. If you've got a photoelectric effect problem and you've written down your givens and in 5 seconds you can't figure out which equation to use the one that's highlighted, because it's almost certainly going to be the one that you use. 2 examples. First one says the work function of a particular metal is 4 EVs. Now remember, the work function of each metal is different because the threshold frequency of each metal is different. The threshold frequency of sodium would be different than the threshold frequency of aluminum, let's say. The threshold or the work function of this particular metal is 4 EVs. We have 2 photons that are incident upon the metal, one with a frequency of 9.9. I'm going to call that the frequency of photon 1, and one with a wavelength of 3.5. I'm going to call that the wavelength of photon 2. 2 different photons here. We want to know if each of these photons will cause photoemission. In other words, we want to know if each of these photons will cause an electron to be ejected.
Do you have to deal with each photon as a problem?
Yes. Yes, absolutely. The question was, do we have to deal with each photon as its own separate problem? And the answer to that question is yes. What I want to do, there's 2 ways to tackle this, but the way that I want to do this is to say E1 is equal to H1 times F1. Well, let's not call it H1 because H is just a constant, right? Planck's constant times F1. If we multiply, what value of Planck's constant do you want to use here, by the way? Yeah, I might as well do the EV one. 4.14 times 10 to the negative 15 EV times seconds times the frequency 1, 9.9 times 10 to the 14. That gives me an E1 value of 4.1 EV. Remember that car on the side of the road? Needed to be hit by a truck at 50 kilometers per hour to be knocked off the road? Truck hits it at 55 kilometers per hour. Is it knocked off the road? Yeah, okay. So this photon has an energy of 4.1 EVs. It needed 4. Is the car knocked off the road? Yeah, the electron is ejected. So the answer to that one would be yes. This is a high enough frequency to cause an electron to be ejected. The second one, we're going to say E2 is equal to hc over lambda 2. hc over lambda because we got the wavelength here, not the frequency. When we solve for E2, we get a value of 3.5 EVs. Okay, now the car is on the side of the road, needs 50 to knock it off into the ditch. I only hit it with 40. Does the car get knocked off into the ditch? No, the electron's not ejected here. Now, there is another way that we could have tackled this question. Does anybody know what it is? Rather than calculate the energy of each photon, we could have taken this and said, got the threshold frequency and saw if that was bigger. And then we could have said, got the threshold wavelength to see if this was smaller. So either way is fine. I kind of like the way that I did it there first, but if what I just said kind of strikes a chord there, then go ahead and do it that way. One more question, and then we call it. Number 4 says the wavelength of EMR on a particular photoelectric surface is 5.0 times 10 to the negative 7 meters. This is not the threshold wavelength. This is not saying this is the wavelength that's required to eject an electron or whatever. This is just the wavelength we have. Back to the truck car example for a second. If the car required 50 kilometers per hour to be knocked off into the ditch, and the truck hit it with 70, we're not saying the threshold is 70. That's just the energy of the truck, right? This is the wavelength of the photon. Maybe it's above, maybe it's below, I don't know. Okay? This is the wavelength of the photon that strikes the surface. What's the maximum speed of the photoelectron if the work function is 0.50 eV? Give you 5 seconds to come up with an equation that uses lambda, W, and V. There they are. Time's up. Yeah. The reason we're going to go to that highlighted one is because those variables don't seem to fit any of them. If you're having trouble, enough trouble that it takes you more than 5 seconds to identify the equation to use, just go straight to that highlighted one, because it's probably going to be the one you end up using here.
The mass of an electron?
Yes. So we're going to say HF is equal to EK max plus W plus the work function. Now, it's confusing here because I don't know what F is, I don't know what EK is. That's okay. We can replace HF with HC over lambda because it's the same thing. We can replace EK with 1/2 mv squared. By the way, we could also replace EK with QV stop, but that wouldn't be relevant in this question. Plus W. We could also replace W with HF0 or HC over lambda max, but that wouldn't be helpful here either. Now, if you remember, I told you yesterday, 90% of the time you can use joules or EVs, whatever you want. But there's 10% of the time when you just got to use joules. This is one of those times. And that's because we're using 1/2 mv squared. We were fine up here with whatever units we wanted. But as soon as we introduce 1/2 mv squared or QV into an equation, we must use joules. If that confuses you at all, what should you do? Always use joules. Joules will always work. It's not always necessary, but it'll always work. So if you're confused about when to use joules, when to use electron volts, just use joules, because it always works for us. We have to use it here. Let's sub in our numbers. We've got 6.63 times 10 to the negative 34 joules seconds. Got to use joules here. Times 3 times 10 to the 8. Divided by the wavelength, which is 5 times 10 to the minus 7. Austin asked, the mass, is that the mass of the electron? Yes, it is. It's an electron that's ejected with kinetic energy, so the mass we use is the mass of the electron. Plus the work function. That work function is 8 times 10 to the negative 20 joules. We can convert electron volts to joules, and that's what you have to do here. You've got to use joules through this whole problem. So let's calculate this now. On the left-hand side, we have 6.63 times 10 to the negative 34 times 3 times 10 to the 8 divided by 5 times 10 to the minus 7. There's the left-hand side there, 3.978 times 10 to the minus 19. Now let's say a half of 9.11. $4.555 times 10 to the minus 31 times v squared plus 8 times 10 to the minus 20. We got to take this over by doing what? Subtracting. Good. So we're going to say 3.978 times 10 to the negative 19. Subtract 8 times 10 to the negative 20. Gives me 3.178 times 10 to the minus 19. Now it's looking easier, right? Take the 4.5 over by Taylor. Dividing, good. .97 times 10 to the 11, and then do what? Yeah, square root it then. And we get 8.35 times 10 to the 5. Really, we should have said V max there. Sometimes we forget to put that little subscript. Not a big deal. That's what it really should be, though. Like, this is it, right? This is it. It's got to be some kind of combination of this. The mathematical problems, that is, have got to be some kind of combination of this. Okay, if it looks confusing, if it's challenging to you at all, do the yellow one, because you can see here how it ended up getting tricky, right? With not only with the equation that doesn't appear on our data sheet, but all these other substitutions that we added into it. Replace HF with HC over lambda, and so on.